let's take a look at number 38. All right, we're in the same section of problems. Now in 38, the directions say to find the derivative of the algebraic function. And what makes 38 tough is not only are we still trying to get a handle on the quotient rule, but all of a sudden they throw in this c instead of a number, where c is a constant. And that seems strange, but it actually is no more difficult. Just c is a number. So we have f of x equals c squared minus x squared divided by c squared plus x squared. Well, this sure looks like a quotient rule problem to me. So to take the derivative of a quotient, it's the bottom times the derivative of the top minus the top times the derivative of the bottom over bottom squared. Okay? So here we go. So f prime of x equals the top, c squared plus x squared, times the derivative of the bottom. And here's where you got to be careful with the c squared. The derivative of c squared is not 2c, because c is a constant. Therefore, c squared is a constant. And the derivative of a constant is 0. Yeah, it is. It's tricky the first time you see it. Can't be tricky after that. Okay? And then the derivative of x squared is 2x. Negative 2x. I forgot the negative sign. Negative 2x. Minus the bottom. No. The top, sorry. Bottom times derivative of the top minus the top, c squared minus x squared, times the derivative of the bottom. Same thing again with the c squared. C is a constant, therefore c squared is a constant. The derivative of a constant is 0. Then the derivative of x squared is 2x. So the bottom times the derivative of the top minus the top times the derivative of the bottom over bottom squared. So c squared plus x squared, quantity squared. All right, you with me on the calculus? Because that's it. That's all the calculus. Now we simplify. Okay? So, there in the top, let's distribute that negative 2x. And when I distribute the negative 2x times c squared, I get negative 2x c squared. Then I distribute the the negative 2x. I don't know why I keep wanting to leave that negative off, but I do. Negative 2x times x squared is negative 2x cubed. Now, look what's going on here that I'm going to highlight in yellow. I need to distribute a negative as well as a 2x. Do that in one step. Think of that as distributing a negative 2x. So, negative 2x times c squared is another negative 2x c squared. And then negative 2x times negative x squared is a positive 2x cubed. Leave the denominator alone. Don't try to multiply all that out. Almost never will we need to multiply all that out in the denominator. Okay? So far, so good? Well, notice something here. I've got a negative 2x cubed and a positive 2x cubed. What's that equal? 0. So then I've got a negative 2xc squared and another negative 2xc squared. How many xc squareds do I have?
4.
Negative 4 of them. So my final answer is negative 4xc squared over c squared plus x squared, quantity squared. Wasn't so bad. Yeah, the C thing is going to mess with you the first time you run into that. All right, we good with 38? Well then, let's jump a little bit ahead and do 74. 74 always comes after 38. And think about it, 74 does come after 30. There's usually some other numbers in between them, but 74 comes after 38. Well, that's just silly. Determine the point at which the graph of the function has a horizontal tangent line. We've worked problems like this before, and we're going to work problems like this all year long. As we learn new ways to find derivatives, we'll learn that method, and then they'll ask us questions like this. Okay? So we know that we can use, in this case, the quotient rule to find the derivative. Once we've found the derivative, what are we going to do with it? Set it equal to 0, because the derivative is a formula to find the slope of the tangent line, and horizontal tangent lines have a slope of 0. All right, so let's find the derivative using the quotient rule. F of x equals x squared divided by x squared plus 1. So f prime of x equals the bottom, x squared plus 1, times the derivative of the top. The derivative of x squared is 2x, minus the top, x squared, times the derivative of the bottom. The derivative of x squared is 2x. The derivative of 1 is 0. Over the bottom squared. So x squared plus 1, quantity squared. Everybody good through that check mark? Okay. Now, notice, because I've noticed, that things that in the previous section were the point of the problem, the derivative, finding the derivative, are now just kind of taken for granted, right? We just got to take it for granted that you can find the derivative of x squared and the derivative of x squared plus 1. That's got to just, it's got to be. And it may not yet. It's got to become just, I can take the derivative of no matter what the coefficient is, no matter what the exponent is. If it's just the combination rule, you got to get really good at that. Okay? So if you're not, you know what you can do? You can go back and rework stuff from the previous section and get better at it. And I know nobody wants to do that, but you know, it's better than struggling with that for the next, how many more months are we in school? Okay? Because you got to get good at it. All right. Now let's simplify this thing. 8. So 2x, 8 more months. Okay. All right. I'm like, so I looked at my paper like, I didn't get 8. Okay. 8 more months of school. All right. So 2x times x squared is 2x cubed. 2x times 1 is 2x. Negative x squared times 2x is negative 2x cubed. The denominator remains x squared plus 1, quantity squared. In the numerator, 2x cubed and a negative 2x cubed is 0. So the only thing left in the numerator is a 2x. So that's our derivative. If all we had to do was find the derivative, we would now be finished. But remember, the derivative is a formula to find the slope of the tangent line. Since we have to have a horizontal tangent line, that means the derivative has to be 0, because the slope of a horizontal line is 0. If they had said, determine the points at which the graph of the function has a slope of 1/3, guess what we would set the derivative equal to? 1/3. Okay? Now, here's the thing. Let's be smart here. So we know that we have a horizontal tangent line when f prime of x equals 0. Look what our f prime of x is. It's a fraction. How does a fraction equal 0? The numerator equals 0. Right? That's how a fraction equals 0. I mean, look. What's that fraction equal? 0. What's that fraction equal? 0. Does the denominator matter? No, other than the fact that it technically can't equal 0. Okay? So, to find where this particular derivative equals 0, set the numerator equal to 0. And then the directions did say point or plural. So once we got x to be 0, go back up here to f of x, put in a 0. It turns out y equals 0 as well, doesn't it? Because we'd get 0 over 1. Okay? Now, y'all follow me on this problem? All right, eventually, we're going to do something like this. Eventually, we're going to need to find where a derivative equals 0 or a derivative does not exist. To find where the derivative equals 0, now let me write it this way. All of a sudden I couldn't spell derivative. Derivative equals 0 when the numerator equals 0. The derivative does not exist when the denominator equals 0. For a rational derivative, when your derivative turns out to be a rational function, so when the how do you spell denominator? Denominator equals 0. So that's the way y'all do that, huh? Okay. So when the denominator equals 0. Do you see why? Okay, good. Good. All right. We cool with 74? All right, look back at the work you did yesterday, the 1 through 34. Which one would you like to see first? Number 3. Yeah, look, number 3 is not an easy one. Just because it's an early number doesn't mean it's an easy problem. All right, use the product rule to differentiate the function. All right, on number 3, we've got h of t equals the cube root of t times the quantity t squared plus 4. Now, I didn't take a step to actually write it, but I thought of that cube root of t as t to the 1/3. Okay? And so we're back to the old, do you take a step to write it, or do you just, do it in your head? I don't know what's best for you. Okay? But you got to think of that as a t to the 1/3. So, and they said use the product rule. So I'm not allowed to multiply it through first to follow the directions. I got to use the product rule. So the product rule says h prime of t will equal the first function, t to the 1/3, times the derivative of the second function. Well, the derivative of t squared is 2t. The derivative of 4 is 0. Plus the second function, t squared plus 4, times the derivative of the first. All right, so this gets complicated here. If I've got t to the 1/3, and I want to take the derivative of that, combination rule, exponent times coefficient, so 1/3 times the coefficient of 1, right? Coefficient of 1, t, subtract 1 from the old exponent. 1/3 minus 1 is negative 2/3. So that's what I got right there. So that's the calculus step. Are you with me on the calculus step? Now we simplify. T to the 1/3 times 2t. Multiply the coefficients. 1 times 2 is 2. Now, multiply factors with the same base, add exponents. So t to the 1/3 times t. Think of that as t to the 1/3 times t to the 3/3. Add the 1/3 and the 3/3, you get 4/3. So I get 2 t to the 4/3. And now on all this nice looking stuff here behind the plus sign. All right, leave the t squared plus 4 alone. But 1/3, that'd be a 1 in the top, a 3 in the bottom. So I don't need to write a factor of 1. So 3 goes to the bottom. And then t to the negative 2/3. Negative exponents, move that factor. Now it's a factor. I need to point that out. Isn't the t to the negative 2/3 times the rest of that? So it is a factor. If it was just a term, I can't move it to the denominator. But since it's a factor, I can move that factor to the denominator, change the exponent to positive. Okay? And look, I need to do that because one of our simplification rules that we're not going to get rid of is no negative exponents unless we just cannot avoid it. Okay? And we will run into some where we can't avoid it. But we can. So we got rid of the negative exponent. So you with me? This far. Okay. And we really need to not be wimps about it, and we need to try to get a common denominator and add this together and get one term. Well, it won't actually be a rational expression because it ends up with a radical in it, but one expression. Okay? All right, so here's what we do. And here's the thought process I'm going through. All right, I've got 3t to the 2/3 as my denominator. So that means I need for the denominator of the other term to also be 3t to the 2/3. So look, if it starts with the denominator of 1 and it becomes a denominator of 3t to the 2/3, didn't I multiply by 3t to the 2/3 over 3t to the 2/3? Because 3t to the 2/3 times 1 gives me the denominator I want. So I got to multiply the top by 3t to the 2/3. Well, 3 times 2 is 6. And then t to the 2/3 times t to the 4/3. Add the exponents. That's t to the 6/3. And what's 6/3? So I get t squared. Everybody go, ooh. If I make it this far, then I'm going to make it. It's going to be all right. I'm going to make it. Okay, because I've done the hard part. And I know, and I even feel silly saying that the hard part's coming up with the least common denominator because you learned about least common denominators in 3rd grade. Ish. But that really is the hard part, isn't it? So let's face it, it is. That is the hardest part. All right. Now we need to combine our numerators over our common denominator. So our common denominator is 3t to the 2/3. So add these numerators together. Well, 6t squared plus t squared is 7t squared plus 4. And I'm happy to get this far. The only reason I changed that t to the 2/3 to a cube root of t squared is because my problem began with a cube root. Okay? So, like on the AP test, multiple choice portion, they would probably have that final answer as the answer choice. Free response portion, they're good with what I have circled. And I am too. Okay? So, but back of the book, it's probably the final answer. It's probably got the cube root of t squared. Okay? I don't know. I didn't look. But that's probably what they have. So, be able to do that even if you don't want to do that, to change it to a cube root, because we started with a cube root. If we had started with exponential notation, then I would quit right there for sure. All right, so y'all scoffed at number 3 because number 3, that was a fairly tough problem. Joseph. Yeah, hall pass. All right? What's next? Which one? 33? All right, let's see. On 33, what do our directions say? Find the derivative. All right. I need to rewrite before I find the derivative, because I can take the derivative of 1 over x using the quotient rule. I can. But remember in section 2, when we would rewrite that as an x to the negative 1 and then use the combination rule? Well, that worked well, didn't it? So I think it's probably easier. And I say probably, and I mean probably, because when you rewrite to change from using one rule to another, it's one of those unintended consequences. You may make one part of it easier, but sometimes that makes it more difficult down the road. So I don't know, but I think it's probably easier to rewrite the 1 over x as an x to the negative 1, and that way I don't have to use the quotient rule inside of my quotient rule. Who wants a quotient rule inside of a quotient rule, right? Yeah, I know. People have messed the cards up. You just have to find it. All right, so that's what I'm going to do. I'm going to rewrite that. Now, I use the quotient rule. And by the way, we will have quotient rule inside a quotient rule, and we'll have product rule inside a quotient rule, and we'll have quotient rule inside a product rule. We'll learn something called the chain rule. We'll have product rule inside of the quotient rule inside of the chain rule. It is, for me. Yeah, we'll learn that next section. All right, so f prime of x equals quotient rule, the bottom, x minus 3, times the derivative of the top. The derivative of 2 is 0. The derivative of negative x to the negative 1. Use the combination rule. So exponent times coefficient, negative 1 times negative 1 is a positive 1. X, subtract 1 from the exponent. Negative 1 minus 1's negative 2. So that's the bottom times the derivative of the top. Minus the top, 2 minus x to the negative 1, times the derivative of the bottom. Well, the derivative of x minus 3, the derivative of x is 1. The derivative of negative 3 is 0. So the derivative of the bottom is just 1. Over the bottom squared. So x minus 3, quantity squared. That's our calculus step. I see frowny faces. Where'd I lose you? The bottom times the derivative of the top minus the top times the derivative of the bottom. So that's the bottom. Any questions on why that's the derivative of the top? Minus sign. The top, so there it is, times the derivative of the bottom. The bottom is x minus 3. The derivative of x is 1. The derivative of negative 3 is 0. So the derivative of the bottom is 1. Bottom squared. Uh-huh.
For the derivative of the top, the reason why it's not negative is because it's 2 minus x derivative.
Right. When I multiply that times that, I get a positive 1. All right. Distribute x to the negative 2 times x. Add the exponents, x to the negative 1. X to the negative 2 times negative 3. Negative 3x to the negative 2. Here, look at the screen. Here, see what I'm circling? I need to distribute a negative, and I need to distribute a 1. So how about distributing a negative 1? That gives me a negative 2 and a positive x to the negative 1. Do not change your denominator. You follow me this far? All right, let's see. There must be some like terms to combine. There's an x to the negative 1, There's another x to the negative 1. We have 2x to the negative 1. We don't have any more x to the negative 2 terms, so copy that one down. We don't have any more constants, so copy that one down. Okay, we good? All right, so I'm sitting here like this. I'm like, okay, I remember old what's-his-face that teaches this class keeps saying we don't leave negative exponents in our answer unless we just can't avoid it. I can't avoid it. That's my answer. Yeah, you can. You can get rid of it. In fact, once I show you how, it's kind of easy. Since I have an x to the negative 2 as my bad math speak here, most negative exponent, that's the one I got to concentrate on getting rid of. So I'm going to multiply by the opposite of an exponent with the opposite of negative 2, exponent of positive 2. So make it x squared. If I multiply the numerator by x squared, no more negative exponents. But if I multiply the numerator by x squared, I got to multiply the denominator by x squared. So I'll multiply by x squared over x squared. And then look, this really is, this is a good, nice technique. It works really well. Distribute x squared times 2x to the negative 1. I'll get 2, then x to the negative 1 times x squared, add the exponents, I get x to the 1, better known as x. So 2x. Then I multiply x squared times negative 3x to the negative 2, so I'll get negative 3, then x to the negative 2 times x squared. Add the exponents. That's an x to the 0. What is x to the 0? 1. What's negative 3 times 1? Negative 3. And then negative 2 times x squared is negative 2x squared. See how well that works? What if I'd have had an x to the negative 7 as my most negative? Multiply that. X to the 7th over x to the 7th. Okay? All right. And the only thing I did next, and this is, you don't necessarily have to. I do want to write it in descending order of exponents. So I want to do negative 2x squared plus 2x minus 3 over this. And then I decided to go ahead and factor a negative out of the numerator. So I put the negative in front, made that a positive 2x squared, a negative 2x, and a positive 3. That's one of those 6 of one, half dozen of the others. So, okay. Yeah, yeah. That's another one of those, if you can, put it in descending order of exponents. Just like you did with quadratics back in the day. Okay. All right. Does that take care of 33? That was fun. You got another one you want to see? 29? Yeah, the radicals make things tough because you got to switch them to exponential and it gets kind of scary. So on 29, we've got f of x equals 2x plus 5 over the square root of x. And you'll see here that I've got this horrible mix of radicals and exponential forms. You know, I'm going to try at least to not end with both, but all right. So while I'm working, I'm not all that worried. Quotient rule, f prime of x equals the bottom, square root of x, or x to the 1/2, times the derivative of the top. The derivative of 2x plus 5 is 2, minus the top, 2x plus 5, times the derivative of the bottom. Now, even though on the paper I've never written down that the square root of x is x to the 1/2, that's the way I have to think of it when I take its derivative, isn't it? That way I can do the power rule to it. So if I need to find the derivative of x to the 1/2, that's going to be 1/2 x, subtract 1 from the exponent, negative 1/2. So that's what I got there. Now here's a nice feature, over the bottom squared. Well, when I square the square root of x, I get x. So the bottom actually got simpler. So look at this first step. Do you have any questions on that first step? Okay. Now, here's another technique that we're going to use quite a bit, and you need to listen carefully. I can distribute this times these two terms, but I kind of get, I don't know, a mess. And a mess is what we get sometimes, right? We just do. So here's a technique we're going to use. See how, even though I wrote that as a square root of x, I've got an x to the 1/2. So see how I've got an x with an exponent as a factor in front of the negative sign, and I've got x with an exponent as a factor behind the negative sign. I can factor out a common factor of x with an exponent on it. So there's my x. Here's where you got to think with me here. Which exponent should I use? Well, let's think. If I had, let me make up an easy example. If I had 2x cubed plus, let's not use 2, let's go with 3x squared, and I needed to factor that. I would factor out an x to the what? Squared, and be left with 2x plus 3. So which exponent did I use? The biggest one or the smallest one? Smallest. We call it greatest common factor, and the greatest throws people off, and if you don't think about it, you'll think, oh, use the big exponent. But you don't, do you? You use the smallest exponent. It's common that matters. See, these two terms both have an x squared. X squared is in common. They don't both have an x cubed. So when I look up here, what both terms have is an x to the negative 1/2. Always use the smallest exponent. When you are factoring out your greatest common factor, always use the smallest exponent, which is going to be the negative one. Okay? So what I factor out then is an x to the negative 1/2. Now, the division gets a little complicated. So you with me on always using the smallest exponent? Now we've got to be careful with the division. So if I've got, let me rewrite that square root of x times 2 as 2x to the 1/2. So if I've got this, and I'm going to divide out an x to the negative 1/2. I know I still have the 2. Now, I said divide out, because I mean divide out. When I divide factors with the same base, I subtract the exponents. So 1/2 minus negative 1/2 is 1. So I'm left with, that's right. So I'm left with a 1. So 2x. With me? That's another, two very, very common mistakes. You choose the bigger exponent instead of the smaller. Next most common mistake is you screw up the division right there. But you got to remember, when you're dividing factors with the same base, you subtract the exponents. So an exponent of 1/2 minus an exponent of negative 1/2 gives you an exponent of 1. Yes. Yep, that's what factoring is, dividing out. All right, copy down the minus sign. Now, look, everything I'm underlining, maybe I shouldn't use red since everything else is red. I will now. Everything I'm underlining here in red is a term. We think of terms being a single entity, but that's a term, okay? And from that term, we're going to divide out the x to the negative 1/2. Well, look, if I have this, and I divide it by x to the negative 1/2, can't I just do that? So I'm left with quantity 2x plus 5 times 1/2. This step right here may give you trouble for a while. You got to fight through it because, again, I feel like I say this all day, every day. It's not going away. We're going to be using this technique in May and between now and May. It's not like today and then again in May. Okay? All right. We okay? Now that this is a factor with a negative exponent, can't I move that to the denominator, make the exponent positive? Okay? So all this step and this step were to get rid of the negative exponent. All right? Because unless we simply cannot avoid it, we don't leave negative exponents in our answer. So that's what these two steps are for. We got rid of the negative exponent. It was complicated, wasn't it? I couldn't just take it at that point and move it down here because it's not a factor. At this point right here, it's not a factor of the numerator, is it? It's just part of a term at that point. So I've got to turn it into a factor before I can move it to the denominator, make the exponent positive. So I move this down below, make the exponent positive, and then I distributed the 1/2. Copy down the 2x, distribute a negative and a 1/2. Distribute that negative, that 1/2. So negative 1/2 times 2x is negative x. Negative 1/2 times 5 is negative 5/2. Oh, thank you. So now that I'm sitting here, the only thing that's really bugging me now is that I've got a fraction in my numerator. Can't keep a fraction in our numerator. So I need to multiply. I need to get rid of the 2. So multiply by 2 over, wait a minute, before I do that. I simplified first, didn't I? 2x minus x is x. Still have the minus 5/2. In the bottom, x to the 1/2 times x is x to the 3/2. Now I'll get rid of the fraction in my numerator. So multiply by 2 over 2. That gives me 2x minus 5 over 2x to the 3/2, which, let's face it, I'm really thrilled to have. Started with radicals. I'll try to end with radicals. Okay, I'm about to say, are there any questions over 29, but I'm figuring there probably still are. So that may be one you have to look at again. It is not against the rules to rework problems because the goal of the work is for what? To learn it. And if you got to do more to learn it, then you got to do more to learn it. Because I'll bet you there's some people that stay after practice and do more extra points, aren't there? Or field goals, or catch extra passes, or work on whatever. See, I know so little about band, I can't even make a decent analogy. But I see you guys out there at 10 o'clock at night. You're doing something. Okay? So, work is work. Which one did you want to see, 32?
Yeah.
All right, on 32, the directions just say to find the derivative. They don't tell me that I have to use a certain rule. So what I did on 32 is I just squared that. Once I squared it, then I could have done this back in section 2. So I squared it, then took the derivative of each term. I'd be good with that. Okay? I went ahead and factored it. Since it started in factored form, I tried to end it in factored form. But if you got there, I'll count it right. Then you can do whichever rule seems most reasonable to you. Do what now? Okay. Yep, the constant multiple rule. So what she's talking about, let's say f of x equals 2 times a bunch of other stuff over 3 times a bunch of other stuff. Yeah, the constant multiple rule says you can just take that 2/3 and put it in front, take the derivative of all the rest, and then your final answer is 2/3 times the derivative of all that rest. All right. Here's what you need to work on. And I know you're busy, but here's what you need to work on. Page 126, 35 through 54, and 59 through 75 odd.